Good afternoon. My name is Caitlin Green, and this is going to be my vlog over these Chapter 6 textbook problems. As you can see on the screen, this is my blank copy of the Chapter 6 textbook problems, but I will be reading and showing you my answers from this copy that I printed out. So with all that stated, let's go ahead and get started. Question 1 shows 42 pregnant rats that are subjected to 8 different intensities of microwave irradiation prior to delivery, which will be the x variable. The dependent variable y will be the litter size. It then asks to display this data in a scatter diagram on a sheet of graph paper with the x on the horizontal axis and the y on the vertical axis. And I thought this problem was pretty straightforward. As you can see, each x variable will go with its corresponding y variable, and you'll just go through and put all these on a graph. Our lowest x variable started off at 1, and our highest was 8, of course, from 1 to high, or 1 to low and 8 to high. And then all the y variables, the highest value was 14, so I made my graph with 1 being the lowest value and 14 being the greatest litter size. And what I ended up figuring out is that it was the less irradiation, or the microwave irradiation, that the rats were subjected to, the greater the litter size that they had. And it ended up giving us a graph that looks something like this. And you can see all the data is pretty well connected together, and that there aren't any outliers or anything like that. And so it's just a very strong inverse relationship. Which brings us on to question 2. It says, by inspection, is this a direct or inverse relationship? And it then asks, is it linear, and are there any obvious outliers? So, like I previously showed you, it was a very strong graph with no outliers. It was a inverse relationship because it was a negative line, and it was pretty much linear because all of the data was pretty much bunched into a line that looks something like this. Question 3 says, determine if the correlation coefficient x and y by using the computational formula in section 6.2. And this question was, I would say, fairly easy once you got all the variables and stuff lined out. However, I put the variables in my calculator, and I did find it's very easy to put the wrong variable in your calculator whenever you're doing it, and so it did take me about 3 tries before I actually got all the right x variables with all the right y variables. So that is definitely something I'm going to consider on the test, just because if one value is messed up, the entire thing is messed up. But I ended up putting all 42 of the variables in the L1 and L2 table, and then I did a 2 variable test, and I ended up finding that sum of x was 187, sum of x squared was 1065, and sum of xy was 1517, and then ey squared was 3942. I guess I just can't speak math today. And the sum of y was 392. And then I ended up putting all of that into the computational formula, and I ended up finding that r equaled negative 0.89, which what this reflects is that it is a very strong inverse or negative relationship. Moving on to question 4, it says, using table B, test the researcher's hypothesis if a predicted inverse relationship between irradiation intensity and litter size at alpha equals 0.01. And as you can see here, it says predicted inverse relationship, which means that they are predicting it to be an inverse relationship. So that means that it's going to only be a one-tailed test because the researcher has an idea, or at least he's hypothesizing that it's going to go in one direction rather than the other. And so because of that, we're going to make our HO, or our null hypothesis, be rho is going to be greater than or equal to 0, and our alternative hypothesis is going to be rho is less than 0. We found that alpha was 0.01, and we take all of this information and take it to table B, and we have to have 3 different parts or 3 different variables to be able to find the R critical in table B. We have to have the number of tails, the alpha, and the just completely lost what I was gonna think, but it's the DF value. I just don't know why I can't think that in my head right now, but I think it's the direction of freedom or something like that. But needless to say, we found that that was 40 because we subtracted the variables available from 2. So it was 42 minus 2 to get 40. And once we did that, we found that R calculated was negative 0.89 in the previous problem. And then we found R critical to be 0.358. And we have to take the absolute value of the R cal, which is one thing that kind of tripped me up. But when we put the absolute value of it, we find that R cal is actually greater than R critical, which means that we have to reject HO and accept H1. And simply the English version is that there is a significant inverse relationship between the irradiation intensity and litter size, which we had already seen in the previous problems because we had actually graphed out the data and found that R cal was very close to a -1. So kind of already knew that, but this just went ahead and set it in stone. And then question 5 says, can the researcher safely conclude that the microwave irradiation causes, say, smaller litter sizes? And this is a very easy mistake to make because looking at all the data that we've found, it is very easy to argue that he could conclude that the irradiation will cause a smaller litter size. However, a big rule is that causation does not equal, or correlation does not equal causation, and causation does not equal correlation. So while he could say it, it would not be true, and so no, the answer is no, because correlation does not equal causation. Okay, moving on to question 6. It says an investigator obtains a R value of 0.381 between the locus of control and performance in a stress task. It then asks, can she reject the null hypothesis of rho equals 0 with the number of participants being 37 and an alpha value of 0.01. So it then asks, which is the next part of the question, is if the investigator had predicted a positive correlation and employed a one-tailed test at 0.01, what would her decision be? So I'm going to split this question up into 2 parts. On the first part, she's already told us that the correlational value of R equals 0.381. So to finish setting up the rest of our equation, we have to find the null hypothesis and the alternative hypothesis. And because she doesn't have a direction of where the how the performance task is going to go, we are going to have a two-tailed test, and so we're going to set the null hypothesis of rho is equal to 0, and the alternative hypothesis, of course, would just be the opposite, so it would be rho would not equal, or would not be equal to 0. We know that our alpha is 0.01, and so now all we have to do is find the Z critical, and we have a two-tailed test. We have an alpha of 0.01, and I just remembered that DF is degrees of freedom, so woohoo there. But we have a DF of 35, and so we take all that information over to table B, and we find that Z critical is 0.418, and as you can see, 0.381 does not equal to 0.418. Which means that we would have to fail to reject HO. So that would be part 1 of the problem. And then we go on to the second part. If the investigator had predicted a positive correlation and employed just a one-tailed test at alpha equals 0.01, what would her decision be? So this is a slightly different problem just because she's employing a one-tailed test and she's predicting a positive correlation, which means that the null hypothesis is going to be rho is less than or equal to 0, and H1 is going to be rho is greater than 0. Our alpha is still the same at 0.01, and we have our cal to be 0.381, and when we find z critical, we take the fact that it's a one-tailed test, an alpha of 0.01, and the degrees of freedom would be 35, and we find that the z critical is actually 0.381 as well, which means that they are in fact equal to each other, and which means that we are going to reject HO and accept H1, because HO is saying that if as long as it's less than or equal to, then we can accept that value, which means that there will be a significant positive relationship in this problem between the locus of control and performance in a stress task. We're going to move on to question 7. So I found these questions to be a bit more easier using the Spearman-Rowe equation, so we'll probably fly through these a little bit faster. Two coaches A and B are ranked 12 defensive backs from films taken from practice. Do the coaches show a significant degree of agreement, 0.05 for alpha, in their rankings? And it tells us to perform a one-tailed test. Now, these problems require a lot of, I don't really want to say backbone setup, but it does take a little bit more to find di and di squared, but it's not really difficult. And as you can see here, these are my values for a, b, and then di squared. I think they're all in the frame there. But we're going to take all those values and put it into the Spearman-Rowe equation. And so we'll have 1 minus, you put in parentheses, 6, the sum of di squared divided by n to the third power minus m. So we end up getting an equation that says 1 is minus 6 times 12 divided by 12 cubed minus 12, and we find that RS equals 0.958, and we find z critical, of course, because we're doing a one-tailed test, and we find that 0.958 is greater than the z critical of 0.506, and so in this decision we will reject HO and accept H1, and simply all that means that there is a significant positive correlation and that it indicates that both coaches are similarly evaluating their defensive quarterbacks. So I don't know what the defensive backs means. I'm not a big sports person though, so I don't know. But yep, that's the answer to question 7. And now finally question 8. It says, given the ranks for the two variables below, compute a RS. Why is the Spearman-Rowe inappropriate for this problem? So we have pretty much the same setup as before, where we have A, B, and we have to find di and di squared. And I'll show you my values and stuff here. Hopefully that's all in there. If not, of course, I'll be submitting a copy of it, so you'll be able to see it that way. But whenever we put that in the equation, we get 1 minus 6 times 145 divided by 10 cubed minus 10. And we end up finding that RS is equal to 0.121. And the reason why this is actually inappropriate for the problem is because the data did not follow a linear pattern. I don't know if you could see it in my di squared values, but essentially they kind of were all over the place, but they ended up making more, I guess, of a parabola shape rather than they did a linear shape, which means that this would not have been an appropriate equation for the data in this problem. But this has been my Chapter 6 textbook problems. Overall, not super difficult. The only thing that I'll have to make sure of is just making sure I put all of my data correctly into the calculator. That way I don't make any small, simple mistakes. Thank you for watching, and I hope you have a good rest of your day. Thanks.